Okay, so welcome everybody to our session called Machine Learning and Human Animation. I'm Shohei Mori from University of Stuttgart, Germany. And for your information, our session consists of 4 presentations, including one DBCG invited paper. So each will have 15 minutes, including QA. So which means that I'm gonna ring the bell, let's say at 10 minutes, 12 minutes, and 15 minutes to keep up with the schedule, okay? So we are gonna start the first paper, which is a HFMGS, half-phase mapping 3D avatar based on real-time HDMT removal, presented by Kangyu Wang. So, the floor is yours.
Hello everyone, my name is Kang Yu Wang. I'm a graduate student from Beihang University. Today, I'm delighted to present my work titled HFMGS, Half-Phase Mapping 3D Alter-Based Real-Time HMD Removal. This work was done together with Jian Wu, Run Defan, Hou Wenzhang, Suiki Imi, and Lili Wang. In extended reality applications such as XR teaching and XR conference, the obstruction caused by XR had muted displays and minimized natural face-to-face interaction. To address this, existing HMD removal methods aim to generate complete unoccluded facial images or videos from HMD occluded inputs. Existing HMD removal methods can be divided into geometry-based methods and image-based methods. Geometry-based methods reconstruct and animate the face using 3D models, which often rely on professional equipment. Image-based methods usually process 2D images directly to fill in the occluded parts, such as those use GNN network, but they usually struggle with 2K needs, real-time processing, and high-fidelity results. In recent years, there has been new progress in digital alters, especially nerf-based and Gaussian-based methods. She proposed a framework with an encoder and a nerf decoder. Qian used the flame framework to drive 3D Gaussian deformation. These works show that nerf and Gaussian-based alters have great potential. They can capture fine facial details and work more effectively than old model-based methods. Let's discuss our motivation. 3D Gaussian splatting constructs high-quality senses with shorter training time and higher time performance. For the challenge of HMD removal, Gaussian-based alters offer fresh insights and a potential solution. So we propose the first framework that combines Gaussian alters for HMD removal, a solution designed to balance real-time performance, high quality, and accessibility without specialized hardware. We now outline the workflow of HFMGS, which consists of 3 key phases. The first is the registration phase, where the user without HMD records approximately 1,000 frames, capturing diverse facial experiences. The second is the training phase, where we optimize model parameters using the data. The third is the real-time HMD removal phase, which operates at approximately 130 FPS. Users input real-time occlusion with HMD, and we generate real-time HMD removal videos. Here is the pipeline of HFMGS, which has 4 steps: pre-processing and encode, half-phase mapping 3D deformation field, correlation-weighted sampling acceleration, and render and supervision, and the Gaussian segregation strategy. In the first step, we remove background and crop the images to return only the lower facial region, which remains unoccluded. We then pass the lower facial images through an encoder to generate a latent code. During training, we use full face reference images for the step. During inference, we encode the lower face from the HMD occluded inputs. Step 2 is the core of HFMGS, as it addresses the challenge of deforming a canonical 3D Gaussian model to match the user's dynamic facial experiences. The deformation of Gaussian alter is defined by 3 parameters: position x, rotation r, and scale s. Our deformation field computes 3 transformations to update these parameters, ensuring the model captures both local and global facial changes. First, for the lower face deformation, we predict deformation offsets for the lower phase Gaussians directly from the latent code. Second, for the upper phase deformation, we introduce half phase mapping, which establish a dependence between upper phase and lower phase Gaussians via two submappings, Gaussian mappings and Parliamentary mapping. For Gaussian mapping, we compute a weight matrix where each entry represents the dependence of an upper phase Gaussian on a lower phase Gaussian. Second, for the Parliamentary mapping, we generate a Parliamentary influence matrix which quantifies how each Parliamentary or each Gaussian affects the mapping. Combining Gaussian mapping and Parliamentary mapping, we propagate the lower phase deformation to the upper phase as shown in the final equation. Third, global deformation. We use a global MLP to predict offsets that capture large-scale facial movements. Finally, we use all three deformations to upgrade the canonical Gaussians, resulting in deformed Gaussians. A major bottleneck is the computational burden from massive Gaussians and their dynamic management during training. To address this, we introduce correlation-weighted sampling to reduce computation. We first compute a correlation weight and rank them for downsampling. After Gaussian mapping, we compute a distance weight between Gaussians for upsampling. To maintain model stability, we prevent Gaussians from crossing the boundary between upper and lower facial regions. We define a split line and a safety margin. Any Gaussian generated within another region is ignored during training, and the two loose terms are used to limit boundary crossing. We evaluated all methods on the ensemble dataset. We compared HFMGS, our method, against the two adapted SOTA methods. Latent outer is a nerve-based method. DECA and the Gaussian outers is a Gaussian-based pipeline that uses DECA to estimate flame parameters. In the result, latent outer performs poorly in capturing the details of the face, such as rings, hair, and teeth shape. Additionally, due to the low accuracy of facial information prediction under HMD occlusion, Gaussian outers shows noticeable jittering and low quality. Here, we also show the comparison video on self-collected data. Our method, HFMGS, shows the highest fidelity among all the methods as well. We use the 6 standard metrics to quantify performance, including MSE, L1 error, PSNR, SSIM, LPIPS, and FPS. As shown in the table, HFMGS outperforms both baselines across all metrics. For PSNR, we reach 30.98 in real-time performance. HFMGS runs at 134 FPS. The half-face mapping model is the heart of our face animation, so we evaluate the impact on HMD removal quantity when individual components of the half-face 3D Gaussian mappings are removed. In the video, our four methods show the highest fidelity, especially in details such as eyebrows and highlight. As shown in the table, our floor model achieves the highest PSNR at 30 and 30.98 and the lowest LPIPS at 0.0779. Properly splitting and maintaining half-face segregation is important for model stability. The Gaussian segregation strategy prevents Gaussians from crossing the boundaries. As shown in the video, Gaussians cross the boundary without segregation strategy, which leads to lower fidelity and unstable training. Finally, we conducted a user study. Users first viewed the ground truth. They were then asked to view and rate the results of different methods. The picture at the bottom shows the two-eye view results of our HMD removal method. And as shown in the right picture, our method, which is marked as easy, shows a significant improvement in the realism of HMD removal result over both SOTA baseline methods. In conclusion, we propose HFMGS, a half-phase mapping 3D GS alter-based HMD removal method. The contributions include a novel HMD removal pipeline based on 3D Gaussian splatting, the half-phase mapping 3D GS, capturing the relationship between the upper and lower phase model, the correlation weight-based sampling for acceleration, the Gaussian cycle creation strategy that ensures Gaussian distribution. However, we still have some limitations. First, we don't make use of additional eye-related data, which may result in limited blinking and eye movement. And our method still relies on the lighting conditions present in the training image. We conduct and drive an individual alter for each user and lacks uniformity among individuals. In future, we will use eye information as additional input during training to better control blinking and eye movement. We will introduce Gaussian-based illumination processing techniques for different senses. And we will also develop a pre-trained facial expression model and fine-tune it for individual users. Thank you for your listening. I'm now happy to take your questions.
So any questions from the floor? Okay, so maybe I can start. When you're comparing with the existing approaches, like you are showing some three videos, right, next to each other, and then one of them was super jittering. I think it was a middle one. And then what was the reason for that? And then why your method is more stable in registration?
Sorry, the sound is a bit little. Can you speak it again?
Yeah. So I think you had a video result, right? Where you are comparing different approaches and yours. And then there were three, as far as I remember, there were three videos next to each other. And then the middle one was super jittering, like moving a lot. And then, but yours was quite stable. So what are the key differences between these two?
Do you refer to this?
Maybe some slides before. Yeah, for example, this one.
This?
Yeah.
In fact, the picture showing this is a little, is a bit, is little, so you can't see the details. But the data show that our method is much better than others. And here, such as hair and eye and highlights are very clear in here to show that our method is the best.
Can you play back the video again?
Yeah.
So my question was like the jittering, the middle one is just moving super fast, right?
Oh.
And yours is quite stable. So what was the key differences?
The DEC and the Gaussian alters has some jittering because it uses DECA to estimate the flame parameters of the model, but with HMD block, it may be hard for us to predict the accurate transformation, like transform and rotation for it. So there are some things like this.
Okay, thank you. So any other questions? I think we still have 2 minutes. Yeah.
Thank you for the nice presentation. I have a question about the experiment part. I think I guess that the upper part that is blocked with HMD and the lower part, including the mouse, can be show the different quantitative results in the for the comparison. So have you tried the separate experiment for the quantitative resource?
Yeah, that's a good question. And we have tried it, but the result is not very well, and we choose this finally.
Okay, so you mean that the lower part and the upper part defeat the previous baselines?
In fact, there's some they can't match very well at some times.
I see. Thank you.
Thank you.
Okay, so my name is Fernanda Miyuki Yamada, and today I'm going to present to you a paper entitled Any Dream Generating Skeleton-Guided Anime Avatars from Text Prompts. Uh, this research was developed with Professor Hiroki Takahashi at the University of Electrocommunications in Japan. So first of all, I would like to present a small introduction. 3D anime avatars are getting more and more popular in augmented and virtual reality and also in metaverse applications. As a research topic, 3D anime avatar generation usually uses image as input, demanding for a huge amount of data for training. Also, the output ends up having lower resolution than the input. In contrast, 3D realistic human avatar generation usually uses text prompt as input, allowing for more freedom. Not only that, but they also use more sophisticated techniques and architectures. So this is a gap in the literature that we identified. And in order to solve this gap, we propose AnyDream as the first text prompt-based framework for generating 3D anime-style avatars. So this is the pipeline for AnyDream. I will explain briefly each block that we have here. We have 3 blocks. The first one is the occlusion-aware skeleton extraction, which contains a parametric model. In our case, we use SMPLX. And through a process of 2D projection and key point extraction, we end up with an image of a skeleton representation of the parametric model in a certain camera view sample. The second block is the skeleton-guided score distillation, which receives the input as like a text prompt, and also the image that we got from the previous block. ControlNet uses these 2 inputs and combines them into a diffusion model that, through a process of score distillation, guides the appearance of the avatar. The last block is the canonical avatar representation, which uses an instant NGP neural network to generate the 3D model for the avatar. So as you can see here, through a process of like exchanging loss values, the appearance of the avatar is changed little by little throughout the epochs. For each epoch, we have a different camera view sample. So this pipeline is inspired by DreamWorks G, which was presented this year. And our main methodological contributions are a LoRa module and also anime style normalization and in-painting loss. So let me explain briefly the methodological contributions. For the anime LoRa module, we used Qt Flat anime LoRa available in Hugging Face. We chose this LoRa because it creates a clear separation between colors that is characteristic of the cell shading effect that is quite popular for the anime aesthetics. In order to encourage even more this type of aesthetic, we also propose the loss function LANI. This loss function is composed by 2 components. The first one being LCP. CP means color palette, and LLA. In this case, LLA means line art. So for the color palette, what we do here is that we get the rendered image of the avatar, and we use k-means clustering to obtain a color palette of that image. Imagine that we have these 3 colors as our predominant colors, and well, then we extend the color palette. So each color has 2 extra tones associated to them. one that is darker and one that is lighter, representing areas of shading and also lit areas. By the end, we also add black and white tones. Black is usually used for line art, while white is used for highlights. After that, for each tone in our augmented color palette, no, sorry, for each pixel in the image, we get the tone of that pixel and find the closest tone in the augmented color palette. Then we subtract both tones to get the difference between them. And we do an average for all the pixels in the image. That's how we get our first component, LCP. For the LLA, for line art, what we do is that we use Sobel edge detection to find parts of the image where we have an abrupt change of colors. And then we also use a normalized grayscale version of the image to identify if the edges between this extreme change of colors, they have darker pixels. And then basically we penalize when the change of colors contains like lighter pixels. So that's how we obtain our final loss function LANI, which is an average value between the two components. So for the experimental setup, I use Python and PyTorch. I run a total of 15,000 epochs, as you can see here in figure 4. The LoRa has an effect of 30% on the weights of the diffusion model, and our evaluation is separated into two phases. First phase is comparing AnyDream against the baseline, DreamWorks G, and the second phase is comparing AnyDream against the state of the art, which is formed by 4 works in the literature, which are all based on image inputs. So to compare AnyDream against DreamWorks G, we prepare 12 text prompts and compare the outputs by semantic, stylization, and anatomical coherence. Here you can see some examples of avatars generated by AnyDream, considering some of the text prompts that we propose. For our first study, which is the semantic alignment with text prompts, we use CLIP, which is a model where you can enter with an image and a text prompt, and it outputs the match between these two inputs. We not only use the text prompt that we use to generate the avatars, we extend the text prompt so they have characteristics that we want our avatars to depict. So before the text prompt, we write front view full body A pose off, and by the end we add with crisp line art and cell shaded colors. So the average clip score that DreamWorks G gets is 33.02, while AnyDream gets an average score of 33.07, indicating that AnyDream has a better semantic alignment with the text prompts. Here we can see an example where AnyDream outperforms DreamWorks G by far. This is due to the face of the character that is more anime-like in AnyDream. The second analysis that we do is regarding the perceptual consistency in stylization. In order to address this, we use VQA, which is another model, but instead of receiving a text prompt, it receives a question. So in our case, we only prepared yes or no questions, and you can see the questions here in the table 1. They are the columns of the table. So we want a positive ratio. We want a high number of yes questions, yes answers. And you can see that for the first 2 questions, AnyDream and DreamWorks G, they perform quite similarly. The big difference comes in the last question that is related to the separation of shadows from base colors. And in this case, AnyDream performs way better. And you can see an example demonstrating how better it is in figure 7, where clearly in AnyDream we have a better separation of the shadowy areas from the base colors. The last test that we do is regarding the preservation of anatomical coherence. In order to do that, we extract key points of front view of the avatar and compare with the key points of our SMPLX model that is used for skeletal guidance. So we use PCK to evaluate the predicted key points, And you can see in table 2 here our results. For a more strict threshold, Anidream performs better, while for a more loose threshold, Dreamworld G gets a better result. This result is not bad because what we wanted to show here is that although we introduce new things into the pipeline of Dreamworld G, they do not compromise the anatomical coherence of the generated avatars. So this shows that the avatars generated by AnyDream are as coherent as Dreamworld's G. Last, I want to compare AnyDream with the state of the art. We select one representative avatar for each method and formulate text prompts to describe the representative avatars. You can see that the spinning ones are generated by AnyDream, and we consider through a visual comparison that AnyDream outperforms the state-of-the-art methods by resolution and also details, level of details. Although I know that ISMAR is focused on AR and VR, I wanted to show some other applications of AnyDream within the anime and manga production industry. First of all, our avatars are fully animatable. They are automatically rigged. So what we have here is that an actor is doing dancing movements, and we extract the key points of this actor and render our avatar on top. We also integrated with background. The second application is the generation of manga panels, where I get an image of the avatar in the position that I want. And I asked GPT-4o to generate the background for the manga panel, and I think it did a pretty good job. Last one is the production of merchandise, where we can print our avatars, position the avatars the way we want, and print figurines for the avatar. So I have one right here. Later, if you want to see, I can show you, give you, so you can touch it. And the advantage here is that we have a consistency in the appearance of these three different types of representation because they are based on the same 3D model. For conclusions, final considerations, AnyDream achieves consistent stylistic fidelity and maintain anatomical coherence. It also outperforms the state-of-the-art methods in level of details. And for future work, what we want to do is to propose more sophisticated prompt processing techniques, dedicated modules for the animation of hair, clothing, and facial features, and also runtime optimization and integration with AR and VR systems. We want to thank the Ministry of Trade, Industry and Energy of the Republic of Korea for the funding. And please access our GitHub. I made the training code public, so you can train you can run the code and generate your own avatars. And also, I left the files so you can print also your own avatars using a 3D printer. So thank you very much, and I want to know if you have any questions for me.
Questions from the floor?
Thank you for your talk. I'm Sumo from KAIST, and have just a brief question about your loss function.
Yes.
Actually, you have averaged the two loss function of color palette and Solvil edge, as I remember.
Yes.
Is there any reason for choosing the same weight between two losses?
No special reason. We ran some initial tests and saw that they were quite proportional. Using the diffusion model that we used a pre-trained diffusion model, and we noticed that the errors that it made regarding the tones were quite close to the errors they made regarding the line art as well. So we didn't see the necessity of establishing different weights for each component. They were quite balanced. So that's why we chose that.
And have you ever tested other weights?
No, not yet.
Oh, I see. Thank you.
Thank you.
Okay, so unfortunately the time is running, so then we have to switch to the next
Ah,
presenter.
okay.
So let's thank again to the speaker.
Okay. Hello everyone. I am Zhimin from the Hong University of Science and Technology and the University of Stuttgart. My paper is called Hahoy Learning Generalized for Joint Representations of the Human Hand and Head Behavior Movements in Extended Reality. So here is the outline of my presentation. I would like to go through the research background, related work, method, results, use cases, discussion, and conclusion. So let's start with the research background. Well, as we know, the way users of the XR will use our hand and head movements to interact in the AR, VR environments. For example, the human hand-head movements that are useful for the interaction target prediction. That also be used for example, the redirected working. And also, we can also recognize the human activities from their hand and head movements. And also, we can also try to do the user identification using the hand and head movements in XR. So what is our motivation? So first of all, we try to jointly modeling the human hand and head movements in XR because they are important for many, because they are important for understanding the human behaviors. And secondly, we want to have a generalizable hand-head representation, which means generalizable means that we want to have a representation that could be used for many other use cases. Okay, let's go to the related work. Human hand and head behavior modeling is a very important topic. For example, people have explored to use Gaussian hidden Markov models to do the human intention estimation, and also using the kinematic regressive models to do the human hand trajectory prediction in the XR environment. Also, people have been trying to use, for example, using the 1D CNN to do the fixation prediction using from the head movement data, and also using 1D CNN and GIO to do the activity recognition using the head movements. So compared with previous works, they usually focus on a single modality, whether it's hand movements or head movements. And they are usually designed for a very specific XR application, as we showed before. So what we do is that first of all, we want to have a joint modeling of the hand and head behaviors. And secondly, we want to have generalizable representations that is not specific for one application that could be applied for various applications. Another line of related work, they do the generalizable representation learning. For example, people have learned the generalizable representation for speech signals, for the human gaze behavior, as well as for the human mouth behavior. So inspired by those kind of representation works, prayer works have learned generalizable representation of speech, of gaze, and of mouth behaviors. We have many successful experiments here. So in our work, we try, inspired by this, we want to learn generalizable representation for hand and head behaviors. Okay, let's go to the method. So the problem formulation is that given a sequence of the hand trajectories and head orientations in the XR environment, we want to have a joint semantic representation of those signals. So to this end, first of all, we use a GCM graph convolutional network, GCM-based semantic encoder that we take the hand trajectory, the head orientations as the input using this GCM-based semantic encoder to learn the semantic representation from those hand-head signals. And we also propose a DIM, denoting diffusion implicit model, DIM to encode the stochastic variations from the signals. We know the signals have many variations. And after this, we would get a stochastic semantic representation of the hand-head behavior. We also have a stochastic representation from the signals. After this, we have the semantic representation and the stochastic representation. We use a DIM-based hand-head decoder that can reconstruct the original signals based on the semantic and stochastic representation. In our method, we also propose an auxiliary training task, which means we use the future prediction, future hand-head movement prediction as an auxiliary training task to improve our representation. So let's see some results. We train our model on an XR dataset called EagleBody, and also we do a cross dataset testing because we want to have a generalizable representation. So we do cross dataset testing. We tested on the ADT and the demo datasets. We use the position arrow for the hand reconstruction. We use the angular arrow for the head orientation reconstruction. In our setting, we use 40 frames as the input. We also compare with the variational autoencoder, namely the VAE, as our baselines. So here's the reconstruction performance of our method and the baselines. We could show that compared with those baselines, our method significantly outperforms those methods in terms of reconstructing the hand and head signals. We have also analyzed the distribution of the arrows, and we could say that in terms of the distribution arrows, the higher the distribution curve, the better the performance. We could say that our method outperforms prior methods very significantly. We also do some ablation study. For example, we replace our GCN encoder to 1DCM, SKM, GIO, or MLP to other encoders, and we also remove the semantic or stochastic representation. We show that all those components are really important for our reconstruction. Okay, so after we get a joint representation, the next part is that what can we do with this? So we show some use cases. The first is that we could identify interpretable hand-head clusters. So what we do is that first we get the semantic representation from the hand and head signals, and then we do a clustering based on the representations. And by doing so, we identify some very commonly occurred patterns in the XR environments. For example, this is to use your two hands to do some activity, and this means that you're just sitting down with your hands bowed, just like what you are doing now. And this is standing up with casually chat while standing, just similar to what I'm doing now. And this is to use your hand to interact with some objects. We also compare with the baseline in terms of the cloud scheme performance, and we show that we are outperforming them in terms of the cloud scheme performance. The next use case that we show is that we could, because we use a diffusion encoder and a different decoder. In our network, our method could be used to do the generation of the new signals. So this is the original signal, and then we have a stochastic representation of the signals. We could do the generation by adding some random noise, Gaussian noise, to the stochastic representation to change the extent of its stochasticity, and also we could also directly replace the representation to a Gaussian noise. We show that our method could be used to generate a variable hand-head data based on our representation. We have also shown some performance on the downstream tasks. We know we have a semantic representation, and then the semantic means that we have many semantic meanings. We tested on the downstream tasks of the user identification and the activity recognition. We show that compared with those baseline methods that outperforms the methods in those downstream tasks. So let's go to the discussion. So we identify some limitations of our work. So first of all, our revelations are limited to the existing XR data sets, which we train on the EagleBody, we tested on the ADT and the demo, and we ignore the scene context information because in our goal is to modeling the hand and head behavior, so we don't take the scene context into our consideration. So in future work, so the first way to extend our work is to evaluate for a broader range of activities and environments. And also we try to explore more applications of the hand-head joint representations. And we would also like to learn joint representations of the hand, head, and the scene context. Okay, so let's come to the conclusion. So the main contributions of our work are listed below. So first of all, we propose another representation learning method that contains a JSON-based semantic encoder, a diffusion-based stochastic encoder, and a diffusion-based handheld decoder. We conduct extensive experiments on 3 public XR datasets that demonstrate the effectiveness of our method. And we also have many experiments on 3 use cases, including the clustering, the generation, and the downstream tasks, to show the effectiveness of our method. Here is the references for our in our presentation. And by the way, I'm now recruiting PhD and postdocs. If you are interested in joining our group, you can contact us. And also, you can find the codes, the source code, and the QR code, or in the link below. So that's all for my presentation. I'm happy to take your questions. Thank you.
Are there any questions from the audience?
Hi, thank you very much for the great talk. I was wondering if you can get the semantic information in runtime from the prediction you like with this method. If you have tested this algorithm in runtime in XR with the
currently we are testing on the existing data sets, the 3 large scale data sets that are publicly available. So we tested, as you say that in the future we would like to explore more applications. Currently we tested on the user identification, activity recognition on those downstream tasks. So we're not testing on for example AR, XR interaction, like that kind of application.
And I wonder regarding this slide, what is the percentage means? It means the accuracy.
Yes. For example, for user identification, that in each data set, for example, they have they have 10 or 20 users. So this means the accuracy of your identification.
Okay, thank you.
Hello, thanks for the wonderful talk. I have a minor question. Can I use the object or the sense semantic information as the additional condition for your method? So like the result could be the hand and head interact with some virtual object in a sense. Thank you.
Yes, that's a good question. As we mentioned that we do not use the scene context information currently, but of course if we and also because our goal is to reconstruct hand-head behaviors, so we only use hand-head as an input. But of course, if we have the scene context, maybe we have a chance to improve the performance of the hand-head behavior modeling. Yeah, and also that's also a way of our future work, as you say. Yeah.
A quick follow-up question on the previous one. How expressive is your method to represent different types of grasps? Did you have any specific evaluation, fine-grained, like a variety of types of grasps you can reconstruct with it?
Currently, we use the 3 XR data sets where we don't test a very specific, for example, a specific handheld movement, but actually in the data set themselves, they cover a lot of XR activities in the XR interactions. So the data set itself covers this, but we don't do a very specific test on a very specific movement.
Is there any other question? So if not, I think we are on time. So let's move on to the next one. Let's give applause to the presenter.
So hello everyone. I'm glad to represent our work from notation to gesture, virtual conductor gesture generation in VR via structure score semantics. I'm Hao Zhengma from Shenzhen MSU BRT University, and the course is Yuxin Shen, Wei Liang, and Yun Jia. So let's begin. So here is a shortcut video of Joe Hash's symphony concert from performance. I believe that everyone presents a symphony concert more or less. But how exactly does a symphony work and how it's connected to the XR? So in a symphony orchestra, the conductor first needs to read the score and understand what is it. But it's not like the simple, but like this one. It's a more complex one. And we should know that the conductor should understand all instruments, what they are playing, and when they begin, and how loud they should pronounce. And they read and understand the whole instrument. And then they convert the information from score to orchestra members through their rich body language. And every note on the score means a specific information, such as the duration and such as the sound. And the orchestra members should interpret the play, ensuring all cohesion or harmonious harmony through the conductor's gesture. And another thing we should know that this is an orchestra sitting template. It's not a specific one, but is a relative position. So which means there are two challenges that determine we should use XR than the flat device. First, an individual angle to observe the symphony orchestra conductor is changed. And such like when I was training, I sit in front of the conductor, but when I'm playing, I might sit next to the conductor. And secondly, the sound of the instrument might influence me, such as when I'm training, if I'm an oboe, the flute sit behind me, so the flute sound come from my back. But when I'm on the stage and the flute might sit next to me, that means the flute sounds will spread from the left or right and will mistake my part if I'm which I'm in. And the only thing I can rely is the conductor's move because he will notice me that it's your turn to play. Upon these issues, when conductor absent, a virtual conductor should maybe a way to fulfill these requests. Well, the related works from now, there were two main types of applications related to conducting in VR system. And the first type is like the Maestro, and it's kind of a VR music game. And the second one is the OSR Virtual Hall provide, and it's more like a 360-degree panoramic video that allow the audience to visit how a symphony work in a VR system. But in the field of scientific research, there are two main types. And first one is rule-based virtual conducting system that is opposed in 2008. And however, it's firstly inconvenient to modify the conducting gestures since the conductor move is designed by the software. And secondly, the player cannot modify the score since the conduct's move is fixed. However, it's also the first VR system in virtual conducting. And secondly, in 2022 and 2023, there were the way that music-driven method is also called audio-driven method that sure that machine learning can be used in a virtual conductor system. But the way of music-driven method is also cannot perceive the hidden musical score such as harmony, and is also lack awareness of the instrument. In summary, neither of these two methods has modeled the deeper musical semantics such from the music score. So upon these, we contribute on three aspects. And the first, we propose a novel score-driven gesture generation framework for structured, iterable, and controllable musical intent modeling. Second, we introduce MSCD, multimodal symphony conductor dataset. It's the first synthesized dataset that includes conducting gestures, audio, and editable scores. The third, we validate the generated gestures from qualitative and quantitative experiments and the user study. Here is the overall architecture of our method, and we take the two-stage to train our model. And we should say that the two-stage method is not our contribution mostly, it's relying on the diffusion conductor. And our work proposed is the score encoding method. In a score, we should notice that one of the most important aspects is musical score encoding. So first, we summarize the information that may conduct to the conductor gesture, such as include this A, I don't know if you can see it clearly, is program and is called instrument, and B, the tempo. C is a whole note, which include the position in the bar, and duration and pitch. And D is a whole bar. It's also called a measure. And E is the key signature. F is a time signature. And G is the emotion marking, expression markings. But we also know that these kinds of score cannot be used for training, so we use PDMX and MuseScore to convert it into a JSON file. It is music XML-like, so it's a standard version. And it includes such information of MetaQuest, that's metadata, some text information, such as the title, the author, and the resolution, a standard time minimum limit, and the tempo, key signature, and time signature. And the time signature is divided into enumerator and the denominator. And the beat is also the cycle of the conductor gesture. And we should say that there is a num that is drum, is down. It means that if it's a down strong beat, so like 4/3 beats is 1, 2, 3, and the first one is the down beat. And moreover, there are most important is the tracks is include program and the pitch uh, and the pitch and duration and some other information. So we will convey this information into the 11, but time signature divided into 2, so it's 12 limits encoding. We also divide the semantics of musical score into 4 parts, including tempo, which might influence the speed of the conductor's movements, and cycle, which determines the cycle of the conductor, and intensity, which might influence the aptitude of the conductor's gesture. And chord, we consider it as a hidden music possibility features. The controlled learning stage network takes concrete embeddings from score encoder and gesture encoder. It optimizes control interpolation loss by aligning positive pairs and performing negative sampling from mismatched instances. We random choose the score from the batch as a negative one. And this is a score encoder is a transformer encoder. And the generative learning stage is incorporate 3 key components: a diffusion-based generative model across multilinear transformer, and a random masking strategy. It was written in paper, so I won't take it long in this page. And next, we will introduce our dataset. This is a statics information of our dataset. It can be shown that we first provide the whole score as an information, but as of writing and as of now, we have collected about 61 paired scores, and for the time video is about 28 hours. But we should know that score is hard to collect, so we have processed about 6 hours and 33 music instruments by 11 conductors. So here is a view of the video. We collect the video from the first, and then we inform it into 1090 20 and times 1080, and also include all conveyed into the 25 FPS. And then we use OpenPose to detect and get the pose of the conductor. And for the score, we collect the PDF format or the MuseScore format. If it is a PDF, so we will convert into a MuseScore hand by hand. It takes a long time. And for the experiments, the quantitative evaluation is shown that our full method is the best in FGD is much more lower, and MSE and diversity doesn't show much lower than the others. Here is the qualitative evaluation, which was a part of Dvorak Symphony No. 9. And it can be seen that the red boundaries and in left and right is a whole measure. And we can see that there is a specific cycle in the gesture presentation. And the green part at the last two, it showed a significant amplitude of the gesture, which means that it does show the information of the music score. We also make an evaluation study. The evaluation study can show that intensity, we mask intensity, the amplitude of average is much more longer than our work. And the cycle mask and choice mask fix the gesture into a specific font. It doesn't move actually. And the tempo mask, it can be shown from the third to the sixth and compared to the work. And it can be shown that no specific cycle. We also made a band shortcut of the video. But there were some issues when we convert the 2D pose to a 3D pose, so it might seem a little bit weird. And the left is a concert scene in an Unreal Engine. For the user study, we make two hypotheses that there were no significant differences in the mean score between the baseline model, which is the audio model, and to our model. And secondly is the no significant differences in mean score between evaluated models and our model. Also between following the two RQs. And in the final, the RQ1 is valid. That's our model shows no significant difference between our model and the audio one, and H2 is rejected, showing a significant difference in mean scores between our proposed model and full ability scores. So which means we find no notable distinction between our with audio one, and full component of ablation is significantly contribute to our model. At last, there were some limitations. We should announce that we still lack of hand gesture and eye contact from conductor to a musician. And secondly, we also requires more comprehensive conductor gesture data set, since the virtual conductor provide about 100 hours and our is 6 hours. And third, we still unmet the needs for real-time feedback and conductor gesture generation, which means if I play oboe and I mistake the wrong time to get into, the conductor should notice me. And we cannot do that yet. And thank you for listening. Here's my email, and GitHub will provide the dataset and the related scores. Oh, thank you. Thank you, everyone.
Maybe one question from the floor.
Thank you so much for your presentation. I'm a little bit confused with the user study. Did you test this with an orchestra? Like, did you test it with a few people to play following the conductor, or what did you evaluate exactly?
We made the user study by a questionnaire, and we put the audio-driven method, the generated gestures, and our model and the full application studies, and we fix this randomly. And we make a questionnaire to send on the WeChat, and we randomly choose is about 100 people, and also they are from different level of the grade and different situation, and we can be seen from this chart. And someone learn the instrument, and some are not, and someone participates and some not.
Okay.
And after it's time limited, so and we actually had a chat with the one who has special skills on the symphony orchestra, and they show that we didn't actually play very well, very better than the audio one. But we do have announced the instrument announcements such as a turn from the conductor and the amplitude like much more higher one.
I also assume facial expression is something that is very important for a conductor to convey emotions to the musicians, right? So that they know if they need to be to carry the dynamics of the song, like go even higher or lower.
Sorry, pardon, I didn't hear clearly.
I was asking, I was saying that also facial expressions for the conductor. I think this was you do not really convey that as well, right? Do you think this is something also that might affect, or like the dynamics of the music itself? Maybe we can we can discuss it.
Okay, so this is the end of our session. So thank you all for joining discussions, and let's give a warm thanks to all the speakers. So enjoy your lunch.